Welcome to the fourth lecture on thermal physics. In this lecture, we're going to continue looking at ideal gases. We're going to be looking at work done on or by a gas, and then we're going to be looking at molar specific heats. This lecture is going to cover sections 19.2 and 19.7 of your textbook. Just a warning, your textbook defines the work as the work done by a gas, whereas we are using the convention of the work done on the gas. So the convention we're going to be using in lectures has the opposite sign to that presented in your textbook. The work presented on the formula sheet is the same as that presented in lectures. So the most important things we saw last lecture, we derived an equation for the temperature of an ideal gas. And so we found that half mv squared RMS, so this is the average kinetic energy per molecule, is equal to 3/2 kBt. And so just rearranging this and replacing the kb with R and the mass of one molecule with the molar mass, we can see that the root mean squared velocity is equal to the square root of 3RT on the molar mass. We then saw the theorem of equipartition of energy, which said that each degree of freedom contributes 1/2 kBt to the energy of a system, where possible degrees of freedom are those associated with translation, rotation, and vibration of molecules. So the total energy of a gas, that's the total amount of energy that any gas can store, is given by 1/2 Fn kBt. We saw that F for a monotonic gas was equal to 3, as it only had the translational degrees of freedom corresponding to the x, y, and z direction. For a diatomic molecule, it had an additional 2 rotational degrees of freedom and 2 vibrational degrees of freedom, so 7 in total, though it can only reach 7 at high enough temperatures. So we looked at the internal energy yesterday. This is the total energy that a gas can store. So here's a definition of it. The internal energy, which is usually written as E subscript internal, is all the energy of the system that is associated with its microscopic components, atoms and molecules, when viewed from a reference frame at rest with respect to the centre of mass of the system. So this means that the average velocity is 0. So we actually made that assumption in kinetic theory yesterday when we said that we were going to assume that it was moving randomly. So why do we need to say when viewed from a reference frame at rest with respect to the centre of mass of the system? If we didn't choose a reference frame at rest with respect to the centre of mass of the system, then there would be a macroscopic movement of the gas cloud through space. And this then brings up questions of relativity. Well, what are we measuring the velocity relative to? And does it mean that one reference frame is preferred over another, so a gas will have a different internal energy in one reference frame over another? And so this is why we define it as in a reference frame where the centre of mass is at rest. So this brings us to heat. Heat is defined as the transfer of energy across the boundary of a system due to a temperature difference between the system and its surroundings. So heat is transferred from the body at the higher temperature to the body at a lower temperature, and it's got the same units as energy, so the joule. So heat is actually an energy transfer, is not a way of storing energy. So sometimes in everyday language we talk about something having a lot of heat, but really heat is an energy transfer, so that's an incorrect usage of that term. So what is the difference between heat and internal energy? Well, internal energy is the energy stored within the system, and heat is the transfer of energy into or out of the system. And what is another way of transferring energy to a system? Earlier in the mechanics topic, you learned about work, which is another way of transferring energy from one body to another body. So people have actually done experiments where they've done work on a system such as water in this container here. This was done by Joule, and you can actually make small changes in the temperature of the water by doing work on it, because you're introducing energy to the system, and so increasing the internal energy and hence increasing the temperature. So this brings us to a really important rule. So we've seen that energy in the system is always conserved. Any transfer of energy into or out of a system will result in a change in the internal energy of the system. And we've said that there's two ways to transfer energy into or out of the system. So this brings us to the first law of thermodynamics. The change in internal energy is equal to the heat transferred into the system plus the work done on the system. So now let's have a bit more of a look at how we can calculate the work done on the system. So first of all, work done on the gas. If we have a gas in the piston such as this, when we use a force to push down on the piston and hence compress the gas, we're doing work on that gas. We're going to consider the case where the piston is pushed down slowly, quasi-statically, so that the gas is always in equilibrium. So the work done is equal to the force which is applied times the displacement of the piston. So if we're considering it quasi-statically, so we're just considering very small increments in this case, so dW, a small increment of work, is equal to F dot ds. So F is the force the piston applies on the gas. So that force is going to be due to the weight of the friction, due to the pressure of the atmosphere pushing on the piston, plus due to any additional applied force. So we can write dW is equal to F dot dy, as the piston's moving in the y direction in this case. So as it's in equilibrium, the force of the gas pushing up on the piston is the same as the force the piston is pushing downwards. And so we have F is equal to minus PA, where this is the applied force. The negative comes about because this is the force from the gas which is acting upwards in the opposite direction. So we have the dW is equal to F dot dy, and F is equal to minus PA. We can just substitute into this equation, and we have that the work done is equal to minus PA dy. And now A dy, that's the surface area times dy, so that's the change in volume of the gas inside this cylinder. dW is equal to minus P dV. So when the gas is compressed, dV is negative, and so the work done is positive. So we actually need to do work on the gas to compress it. As a gas expands, dV is positive, and so dW is negative. So as the gas expands, it's the gas itself which is doing the work. And so the energy contained within the gas decreases. So we've just written dW is equal to minus P dV. This is the differential form. To solve it, we need to integrate. So W is equal to minus the change in the volume times the pressure. So minus the integral of P dV. So to solve this integral, we can just work out the area underneath the curve. Usually in physics, that's the easiest way to do it. You're generally given fairly simple geometric shapes, and so it's fairly easy just to work out the area underneath the curve. And there will be a few occasions where you may have to actually integrate. So let's consider these three different situations here. In each of these situations, we're going from the same initial state to the same final state, but we're getting there through different means. In this first case, we're keeping the pressure constant and changing the volume, and then keeping the volume constant and changing the pressure. You can see the amount of work done in this case is just the area under the curve here. As this is a line directly up and volume isn't changing, there's no work done there. So this is a relatively small amount of work done. In this second case, we initially keep the volume constant and then we keep the pressure constant. And the work done in this case is actually much larger, as the area under the curve is much larger. And in this case, it's the case in between. So what you can see is that the work is actually dependent on the path we choose to get from an initial state to a final state. So the work isn't fixed, it's dependent upon the path we choose to take between two states. So an example, how much work is done on the ideal gas below? So we're going from state A to state B. Okay, so the question asks us to calculate the work done as we go from A to B. So we can see that in this case the volume's going from 1 litre to 2.2 litres. And so this is an expansion. So as it's expanding, it's the gas which is doing the work, and so the work done on the gas is going to be negative. So the work done is given by minus the integral from the initial volume, so that's the volume at A, to the volume at B, P dot dV. And the easiest way to solve this integral is to work out the area underneath the curve here. So that's this area in here. So this is a trapezium. So minus, and now to work out the height for a trapezium, we can just take the average height. So it's going from 7 atmospheres down to 2 atmospheres. So 7 plus 2 over 2 times 1.01 times 10 to the 5. This number here is to get it into pascals, the standard units for pressure. And then we need to times that by the width of our trapezium, which is the 2.2 minus 1. And now this is in litres, but our SI units for volume are meters cubed. So we times that by 10 to the minus 3 to convert it into meters cubed. Okay, solving this on the calculator, we end up with minus 545.4 joules. And so we can really only measure this to two significant figures. So let's give our final answer to two significant figures. This is minus 550 joules. Now, the second part of this question says, does the temperature of the gas change? Well, if the temperature was not to change, then we know this is an ideal gas. So we have PV is equal to nRT, and all of this would be constant. So this would be constant. So we'd have P is equal to some constant over V. But this is in fact a straight line. It's not a hyperbola. So we know that T is not constant, as this is a straight line. Okay, now we're asked about the case where we're going from A to B, which is exactly the same as the previous case, except that the arrow is in the opposite direction. So in this case, the gas is undergoing a compression. So the numbers involved in the calculations are all going to be the same. The only difference is that negative sign. So the answer to this case is 550 joules of work is done on the gas. So we have to actually do work on it to compress it. So if you want to practice calculating the work, for 1121 try set 4 question 6, and for 1131 try set 4 question 8. The specific heat of a gas is the amount of energy we need to add to raise 1 mole of that gas by 1 Kelvin. We've just said that points at the same temperature will be found along a hyperbola on the PV diagram. So you can see here we've got 2 blue isotherms. So all the points along each of these blue lines are at the same temperature. So to get from the initial point at temperature T to one of these final points at temperature T plus delta T, the temperature has changed by an amount delta T, and we've had to add in a fixed amount of energy. Because the temperature has changed by the same amount, going from this isotherm to this isotherm, independent of the path, the internal energy has changed by a fixed amount. So the internal energy is set by the temperature of the initial state and the temperature of the final state. But the work done to get from one isotherm to another isotherm actually depends on which path we choose, because the work is the area underneath the curve. So the work and the heat added are dependent on the path that we choose. So the internal energy of any state is given by, for a monotonic gas, 3 over 2 nkBT. For any gas, we'd have an F here instead of the 3. So the change in internal energy is 3 over 2 nkB delta T. And so if the temperature changes by a fixed amount, the internal energy changes a fixed amount. But the work done is dependent upon the path, so Q is also dependent upon the path. So we can write that Q is equal to the specific heat times the change in temperature. But this is really the definition of the specific heat here. It's related to the amount of heat added and how that changes the temperature of the gas. It's more useful to use the molar specific heat, which is the amount of heat we need to add per mole of the gas to change the temperature 1 Kelvin or 1 degree C. So at constant volume, we write the heat added is equal to NCV delta T. So this is the molar specific heat at constant volume. And at constant pressure, we write Q is equal to NCP delta T. The constant volume case is when we're going from I to F. In that case, the volume here is not changing. The constant pressure case is when we're going from I to F dash. In that case, the pressure here is not changing. Here's a question for you to think about. Which one's going to be larger, the specific heat at constant volume or the specific heat at constant pressure? Here's the hint. The change in internal energy is equal to Q plus W. Q is defined as NCV delta T for the constant volume case and as NCP delta T for the constant temperature case, and the work is equal to minus VI to VF P dV. Okay, so to answer this, the change in internal energy is the same for both cases, but the work done is different between the two cases. For the constant volume case, there is no work done, so the change in internal energy is just going to be due to the heat added. For the constant pressure case, the work done is equal to the area under the curve here. But in this case, the gas is actually expanding, and so the gas is doing the work, and so that is a negative work term. So for the CP case, Q actually needs to be larger because there has to be enough to overcome this negative work term and then get it up to the same change in internal energy. So Q is larger for the constant pressure case. Okay, let's look at the constant volume case in more detail. In this case, work is equal to 0 as the volume is not changing. So the change in internal energy is just equal to the heat added. And Q we've defined as NCV delta T. This was how we defined the molar specific heat at constant volume. And so the change in internal energy is just NCV delta T. Now we can rearrange this to write CV is equal to 1 over N times the change in internal energy over the change in temperature. So that's just the same statement. Now what we're going to do is we're going to substitute in for the change in internal energy. We know for a monotonic gas that the change in internal energy is given by 3 over 2 nkB delta T. Or if we have the number of moles, it's 3 over 2 nR delta T. So now we're just going to substitute this expression into here. And we end up with CV is equal to 1 over N, 3 over 2 nR. The n's will cancel, giving us 3 over 2 R. But R is just a number, it's 8.314. So we can substitute that in and solve, and we get that CV is equal to 12.47 joules per mole per Kelvin. Now we can actually check this against experimental data because it's possible to measure how much energy we need to put into a gas to raise its temperature. So for helium we've got 12.5, which is the same as 12.47 within the significant figures. Argon also 12.5. Neon is a bit off, 12.7, and then krypton's 12.3. As the masses of these monotonic atoms gets larger, approximations from the kinetic theory actually break down a bit because we've got a bigger electron cloud around those atoms, and we made the assumption that the only forces involved are from the elastic collisions of the particles off each other, as the electron cloud gets bigger, there's other forces involved as well, other electrostatic forces, which we're not taking into account in our model. So that's why the numbers are more off for the heavier atoms. So at constant volume, we've got CV is equal to 1 on n times the change in internal energy over the change in temperature. So for the general case of a gas, instead of having the 3, we have the F, the number of degrees of freedom. So just substituting this into here, and remember this is just a delta T, so these will cancel. We end up with CV is equal to 1/2 FR. So this equation is provided for you on the formula sheet. Okay, now this is an interesting graph. It shows us for hydrogen gas, H2, how the CV varies as the temperature varies. So you can see at low temperatures, below around about 100 kelvins, the CV is equal to 3 on 2R. That's due to the 3 degrees of freedom. Between around about 100 kelvins and around about 1000 kelvins, we end up with the CV is equal to 5 over 2R. And then as we increase the temperature above that, we end up with the 7 over 2R. So this has been measured experimentally, and that's evidence of what we were saying last lecture with the theorem of equipartition of energy, how for low temperatures for a diatomic we've only got the 3 translational, then at mid-range temperatures we have an additional 2 rotational, and then at higher temperatures we have an additional 2 vibrational modes of freedom. So now let's look at the constant pressure case. So this is the case where we're going from I to F dash, which is a bit more complicated because we now have work done as well as the heat flow. So the change in internal energy is equal to NCP delta T. This is our expression for Q. It's how we defined the molar specific heat at constant pressure. And the work done is equal to negative, because this is an expansion, P times the change in volume. And now just from our ideal gas law, in this case the only things which are changing are the volume and the temperature, as we're keeping the pressure constant. So we've got that our change P delta V is equal to NR delta T, the change in temperature. So we can just substitute this into this formula here. And so we have the change in internal energy is equal to NCP delta T minus NR delta T. And now remember that we said that the change in internal energy didn't matter which path we took. So this change in internal energy is the same as the change in internal energy when going from I to F, or the constant volume case. So this is equal to NCV delta T. So now what we can do is solve these two equations simultaneously, as they're both equal to the change in internal energy. And so we have NCV delta T is equal to NCP delta T minus NR delta T. All our N's and our delta T's will cancel off, giving us CP minus CV is equal to R, or CV is equal to CP minus R. So for a monotonic gas, this turns out to be CP is equal to 5 over 2R, because remember CV was 3 over 2R. And so solving that, we get CP is equal to 20.785. We can check this against the experimental data. And we get 20.8 for helium, argon, neon and krypton, which is all in agreement with that 20.785. If you want to practice using these formulas, you should try homework set 4 for Phys 1131, question 10. Okay, so I'm going to introduce this now. You'll be meeting gamma again later, but gamma is just the ratio of the specific heats. So it's CP on CV. So for a monotonic gas, if you were asked to find gamma, you just substitute in CP, which is 5 on 2R, CV, which is 3 on 2R, so you end up with 5 on 3, which is 1.67. You'll be meeting gamma when we learn about adiabatic processes. Now we're on to some questions to practice using these formulas. So 1 mole of an ideal diatomic gas goes from A to C along the diagonal path shown on the next slide. During the transition, what is the change in the internal energy of the gas? And how much energy is added to the gas as heat. And then part C says how much heat is required if it goes from A to C along the indirect path A, B, C. So here's our diagram. Okay, so we've got our diagram here. Let's just recap what the question asked. Part A said what's the change in internal energy from A to C. Part B said how much heat is added going directly from A to C. And part C said how much heat is added if we go from A to B to C. And we're told that we have 1 mole of a diatomic gas. Okay, now questions like this are always much easier if we can use the first law of thermodynamics, that the change in internal energy is equal to Q plus W. Now in this first case, going from A to C, fortunately we can't use this as we have no information about Q. So while W can be calculated relatively easily, that's not going to help us find the internal energy, because this is not the CP case nor the CV case. We don't have constant pressure or volume. So we're going to have to go about this the hard way, which is to use the ideal gas law. PV is equal to nRT. We can use this to find the temperature at A and the temperature at C, and then we can use our other equation for the change in internal energy, that it's equal to F over 2 nR times the change in temperature. Okay, so the temperature at A is equal to the pressure at A times the volume at A over nR. The pressure at A here is 5 kilopascals, so that's 5,000. The volume at A is 2 meters cubed. The number of moles is 1, and R is 8.314. So this is 10,000 divided by 8.314. Solving that on the calculator, we get 1,202 kelvins. The temperature at C is equal to PCVC over nR. The pressure at C is 2,000 pascals. The volume at C is 4 meters cubed. There's 1 mole involved, and R is 8.314. Solving that on the calculator, we get 962 kelvins. Now, both these cases are around about 1,000 kelvins, which makes it a bit hard to tell if F is going to be 5 or if F is going to be 7. You wouldn't lose marks for assuming either way, but let's assume that this means F is equal to 7. Now, the temperature at A is higher than the temperature at C, which tells us that the internal energy is actually decreasing. So the change in internal energy from A to C is equal to F over 2, so that's 7 over 2, times N, which is 1, times R, 8.314, times the change in temperature, which is the final temperature, minus the initial temperature. Solving that on the calculator, we end up with minus 6,984 joules. So presenting this answer, we should just give it to 2 significant figures because it's hard reading very accurately off this graph. So we can write this as minus 7.0 kilojoules. Okay, so that's part A. Now part B said how much heat is added going from A to C. We can't use the constant pressure or constant volume formulas to find the heat because pressure and volume are not constant. So what we'll need to do is use this first law of thermodynamics. We now have the change in internal energy, so if we work out the work, then we can work out the heat. So the work done is equal to negative the integral from VA to VC P dV, which is just the area under this graph here. And the gas is expanding, the volume's increasing, so it's going to be a negative work. So this is minus Now, we can take the average height of the trapezium, the average of 5 and 2, so it's 5,000 plus 2,000 over 2, and then we times this by the width of our trapezium, which is 4 minus 2, or 2. Those cancel, and so we end up with minus 7,000 joules, or minus 7.0 kilojoules. Okay, now we've been asked to find how much heat is added. Q is equal to the change in internal energy minus the work done. So in this case, we should actually use our exact number here, minus 6,984 minus 7,000. So these add together, they almost cancel out, and we end up with 16 joules of heat added. Okay, part C says how much heat is added going from A to B to C. Now there's two ways to do this question. The easy way is to use the first law of thermodynamics. We know the change in internal energy between A and C, and that change in internal energy is independent of the path. The hard way to do it is to use CP for this case to get the heat added, and then CV for this case. In that case, we'd need to work out the temperature at B. So just for completeness, let's do it both ways. In an exam, I recommend that you use the first way. Okay, so Q is equal to the change in internal energy minus W, and this is from A to B to C, from A to B to C. Okay, so we need to work out the work. The work done from A to B is equal to minus the volume at A, the volume at B, P dV. It's an expansion, and it's just equal to the area underneath this rectangle here. So that's equal to minus 5,000 times the width of the rectangle, which is 2. So that's minus 10,000 joules. And then the work from B to C is equal to 0 as the volume's not changing. So the work from A to B to C is equal to minus 10,000 joules. So just substituting everything in here, the change in internal energy is the same, the minus 6,984, and the work is the 10,000. Solving that on the calculator, we end up with 3,016 joules, which is equal to 3.0 kilojoules. To two significant figures. Okay, so we said that Q going from A to B to C was equal to 3.0 kilojoules. Now let's calculate it the second way, just to show you that this way is longer and is probably not such a good idea. We can work out the heat going from A to B using, from A to B we've got constant pressure, so it's NCP delta T. So we need to know the change in temperature between these two. So to start with, we need to work out the temperature at B, which is equal to PB VB over NR. The pressure at B is 5,000. The volume at B is 4, and this is over 1 times 8.314, which gives us 2,406 kelvins. And now we're told that this is a diatomic gas, so CP, and it's at high temperatures, is equal to R plus CV, which is F over 2R. So this is 7 over 2 plus 2 over 2, 9 over 2, R, which is equal to 37.413 joules per mole per Kelvin. Okay, so Q from A to B is equal to 1 times 37.413 times the change in temperature. The final temperature is 24,006. The initial temperature, the temperature at A, we calculated earlier, and we found that it was 1,202. So this is equal to 45,045 joules. Okay, now what we need to do is work out how much heat is added going from B to C. So Q from B to C is equal to N, this is the constant volume case, times delta T. CV for constant volume, this is all at high temperatures, so we'll assume F is 7. So we've got CV is equal to F on 2R, 7 over 2R, which is equal to 29.099 joules per mole per Kelvin. Okay, so substituting in 1 times 29.099. Now the final temperature was the temperature at C, which we said was 962, minus the initial temperature, the temperature at B, which was 24,006. Substituting in, we end up with minus 42,019 joules. Okay, so Q from A to B to C, we just need to add these two. So this is the 45,000 minus the 42,000. You can see that's going to give us 3,026, which to two significant figures is 3.0 kilojoules. So that gave us the same answer as we got using the first law of thermodynamics. Write that neatly. So that gives us the same as we got using the first law of thermodynamics, but as you can see, where possible, use the first law of thermodynamics because it's a much faster way to solve these questions. Okay, next question. The temperature of 3 moles of an ideal diatomic gas is increased by 40 degrees C without the pressure of the gas changing. The molecules in the gas rotate but do not oscillate. Okay, so it's diatomic, it's rotating and not oscillating. So rotation gives it 2 degrees of freedom. If it's rotating, it's also translating, so that's 3. So it's got 5 degrees of freedom. How much energy is transferred to the gas as heat is part A. Part B, what is the change in internal energy of the gas? Part C, how much work is done on the gas? And part D, how much does the rotational kinetic energy of the gas change? Okay, so we're told it was a diatomic gas and it had, 5 degrees of freedom. The change in temperature is equal to 40 degrees C. There are 3 moles of the gas involved, and this is a constant pressure process. So if we have a PV diagram, it looks something like this. And part A, we were asked, how much energy is transferred to the gas as heat? Okay, in this case, there's no easy way to use the first law of thermodynamics because we're not told anything about the internal energies or what the initial temperatures were or the initial volumes. So we'll need to use Q is equal to N Cp delta T. Cp is the molar heat at constant pressure. So we're told that there's 3 moles. Now Cp is equal to R plus F over 2R, and in this case F is 5, so this is 7 over 2R, which is 29.099, so substituting that in, 29.099, and the change in temperature is 40. So now we can just enter all this into the calculator. When we do that, we get 3,492 joules. So this is only to 2 significant figures. So let's give our answer to 2 significant figures. It's 3.5 kilojoules. Okay, now we're asked to calculate in part B the change in internal energy of the gas. So we'll need to use the formula for the change in internal energy. It's F over 2 nR delta T. We know what all these things are in this case. So we've got 5 over 2 times 3.00 times 8.314 times 40. Solving this on the calculator, we end up with 2,494 joules, which is equal to 2.5 kilojoules. Part C asks us how much work is done on the gas. So now we can finally use our first law of thermodynamics. Work is equal to the change in internal energy minus the heat added. So this is 2494 minus 3492. Solving that on the calculator, we end up with minus 998 joules, which is equal to minus 1.0 kilojoules, to two significant figures. And this is work done on the gas, which means that plus 1 kilojoules of work is done by the gas. And then part D said what was the change in the rotational kinetic energy of the gas. Well, the gas has 5 ways of storing energy because the number of degrees of freedom is 5. So 3 of those ways are translational and 2 are rotational. So the change in kinetic energy is the change in rotational kinetic energy is going to be 2/5 of the change in the internal energy. So it'll be 2/5 times 2.5 kilojoules, which is 1.0 kilojoules. So the other way to do it would be to substitute in here just a 2, just to calculate for the rotational degrees of freedom. And the final question, the temperature of 2 moles of an ideal monotonic gas is raised by 15 kelvins at constant volume. What are A, the work done by the gas, B, the energy transferred as heat, C, the change in the internal energy of the gas, and D, the change in the average kinetic energy per atom? To answer this question, we know that we've got constant volume, we've got 2 moles of gas, and we've got that the change in temperature is equal to 15 kelvins. So part A asks what W is done by the gas. So this would have the opposite sign to the work done on the gas. But as it's a constant volume process, we know that the work done is 0. Part B asks us how much energy is transferred as heat. So to work this out, we'll need to use Q is equal to NCV delta T. Now it's a monotonic gas, which tells us F is equal to 3. So CV is equal to F over 2R, which is 3 over 2 times 8.314. Solving that on the calculator, we get 12.471. Okay, so Q is equal to 2.00, that's N, times this 12.471 times the change in temperature, which is the 15. Solving that, we end up with 374 joules of heat is added to the system. Part C says what is the change in internal energy? Well, we can just use the first law. The change in internal energy is equal to the heat added plus the work done on the gas. The work done is 0, so this is just equal to the heat added, which is 374 joules. And then part D says what is the change in the kinetic energy per molecule. So the change in kinetic energy is the same as the change in internal energy. So we just need to work out how much does the internal energy change per molecule. So we take the internal energy and divide it by the number of molecules. So there's 2 moles, and each mole has 6.022 times 10 to the 23 molecules, or atoms in this case, in it. So solving that on the calculator, we get 3.11 times 10 to the minus 22 joules per atom. And that's the end of this lecture.